In just 5 years, mobile gaming has rivaled the complexity and quality of games found on consoles and computers. Now we can see high-resolution 3D models with 100,000 polygons or even more. But rendering a scene with an enormous number of polygons can consume significant memory and lead to an extremely fast battery draining on mobile devices. There are techniques that reduce the memory footprint for mesh geometry data. One technique is the geometry instancing, which draws the same mesh multiple times without duplicating the vertex data. Tessellation technique allows to refine mesh geometry on the render pipeline without requiring an allocation of an additional memory to hold the resulting vertices and normals. In this presentation, we will demonstrate the use of two techniques at once, and we will look at how to do geometry tessellation on the Apple GPU using the Metal API. Tessellation operates on patches, with each patch representing an arbitrary arrangement of geometry defined by a collection of control points. We introduce curved point normal triangles or short PN triangles as patches. Each PN triangle replaces the original flat triangle by a curved shape that is retriangulated into a programmable number of small subtriangles. The control points and normals for a PN triangle are generated offline without any calculations at engine runtime. The geometry of a PN triangle defined as one cubic Bezier patch. We stream patch control points, marked in green, as an ordinary vertex buffer data using data deduplication. Other control points, marked in red, are streamed as an additional data structure packed in a separate patch buffer. Thus, we can combine two rendering techniques, low-resolution geometry rendering and geometry tessellation technique. For example, when we render a shadow map, we do not need high-resolution mesh geometry because shadow edges are blurred in a post-processing render pass. Per patch tessellation factors specify how much each patch is subdivided by the tessellator. The tessellator is a fixed function pipeline stage that creates a sampling pattern of the patch surface and generates graphics primitives that connect these samples. For a triangle patch, we specify three edge tessellation factors, which describe how the outer edge is refined, and one inside tessellation factor, which describes the subdivision of the interior region of the patch. We use the compute shader to calculate the tessellation factors for each patch. For patches that are far away from the camera origin, we set the tessellation factor to the minimum value. For those patches that are outside of the viewing frustum, we set the factor to 0, then the tessellator discards the patch. First, the tessellation factors of the patches are calculated in a compute shader. Then, tessellation factors get consumed by the tessellator, which produces the subdivided set of triangles and passes it down the pipeline to the post-tessellation vertex function. In the next step, we use the post-tessellation vertex function. Unlike the ordinary vertex function, which operates on vertex data, post-tessellation vertex function is a function that calculates the vertex data for each patch surface sample produced by the tessellator. The post-tessellation vertex function generates the final vertex data for the tessellated triangles. After the post-tessellation vertex function has completed execution, the tessellated primitives are passed to the rasterizer and the remaining stages of the render pipeline get executed. Let's get a closer look at the post-tessellation vertex function. Post-tessellation vertex functions are prefixed with a patch attribute. The first attribute parameter indicates the patch type, triangle, while the second parameter is the number of control points per patch. We use 3 control points per patch. The vertex function takes a parameter with a stage in attribute to indicate that we want to fetch control point attributes. Unlike ordinary vertex attributes, control points are specified as the patch control point template type. The next parameter is a patch ID, which identifies the patch structure from the patch data buffer. The patch structure is a set of PN triangle control points. The next difference between an ordinary vertex function and a post-tessellation vertex function is the position in patch attribute. A parameter with the position in patch attribute contains barycentric coordinates of the current vertex in the patch. The next parameter is the instance identifier for repeating mesh geometry. Now we use all function inputs to calculate the tessellated vertex data. In this demo, we see a difference when rendering a cylinder mesh without tessellation technique, and then we pass cylinder mesh into the GPU tessellation pipeline. In the second case, the silhouette of the tessellated cylinder mesh looks much better. In this video, we see how the original, even low-resolution 3D model looks great with tessellation rendering technique.